Okay, everyone, let's start to settle down for the last session. Please take your seat. There will be plenty of opportunities to continue chatting after the session is over. Okay, we don't want to run too late because we have some official announcements at the end. So after the series of applause after the session, don't run away. There will be some announcements. Some of them probably exciting, if you were in student research competition, for example. And the general chairs and other organizers want to say a couple of words. So let's start. This is the last technical session of the main conference of SIGCOMM' 2022. I'm your session chair, Sergey Gorinsky from MDN Networks Institute in Madrid, Spain. The session, again, combines kind of two related but different topics of home networking and video delivery. We have 5 talks. Unfortunately, 2 of them are online, virtual, the first and the fourth, but we conclude with the in-person talk at the end. So this is good news. So let me introduce the first presenter, the remote presenter. Chijay Kai is a student of Rachid Agarwal at Cornell University. Well, he's doing various things, you will see, but I think more specifically than the interest in network systems, he works on the Terabit Ethernet. So let's play the presentation first.
I'm going to tell you about how to re-architect the host network stack for microsecond scale tail latency and terabit Ethernet. It's a well-known fact that today's host network stacks have many limitations. For example, let's look at the most widely deployed host network stack today, the Linux network stack. Some of the frequently cited problems with Linux network stack include its inefficient packet processing pipeline, its inability to provide performance isolation when applications are co-located, its rigid and complex implementation, which makes it difficult to introduce changes, its inefficient transfer protocols, and many others. This long list of limitations has led to many interesting debates on various design aspects of the host network stack. This includes debates on what the application interface should be, semantics exposed to the application, and finally, the place where the network stack is implemented. In this work, we show that many of the limitations of the host network stack are not rooted in placement, interface, or semantics, but rather in the core architecture of the network stack itself. Let's look at the architecture of today's host network stacks. The fundamental abstractions that today's network stack are based is on classical pipe abstractions, where each application or thread submits the data to one end of the pipe, and the network stack attempts to deliver to the other end of that pipe. Let's focus on single-end host. The pipe abstraction has three properties. First, each application or network socket has its own dedicated pipe with its own independent instance of packet processing pipeline. Second, packet processing at the very stage of the pipeline is highly coupled with a cores on which the corresponding applications are running. Third, the host resource allocated to each pipe are statically determined during pipe creation time and remains unchanged, independent of other coexisting pipes and dynamic resource availability at the host. In this work, we show that the dedicated, tightly integrated, and static nature of today's host network stack architecture is the root cause of many other problems. In particular, it precludes them from fully exploiting the capability of modern hardware. The remainder of this talk is organized as follows. First, we experimentally demonstrate the problem with dedicated, tightly integrated, and static pipelines. Next, we present NetChannel, a new host network stack architecture that disaggregates the packet processing pipeline. Finally, we demonstrate that NetChannel can achieve several new operating points that were previously unachievable by evaluating prototype implementations of NetChannel. To demonstrate the problem with today's architecture, we use a simple experimental setup with two servers directly connected by a 100 gigabit link. We run an application on a single CPU core that sends a single long flows. Here, we find that the link bandwidth is larger than per core throughput achieved by the network stack. While we can try to increase per core performance, there will always become a bottleneck at some point for high bandwidth link. Hence, the network stack needs to utilize multiple cores to saturate link bandwidth. Look at the breakdown of where CPU cycles are spent in the network stack. We see that nearly 70% of CPU cycles are spent in interface level processing. In this example, this includes the cost of buffering and copying data between user space and the kernel. Due to the static and dedicated nature of today's architecture, the number of cores that can be used for this processing is limited. In this example, all of this processing is bounded to the application core, even though other idle CPU cores are available. Our ideal network stack should be able to dynamically scale the number of cores used for interface-level processing based on the current resource availability at the host. Now, let's look at the case of a short message. Even here, the link bandwidth is larger than per core throughput. Look at the CPU breakdown. We see that network layer processing is the main contributor. The number of cores that can be used for this processing is limited by the number of connections due to the static nature of a pipeline. In this example, all of this processing is limited to a single CPU core since there is only one connection. All of this processing is again limited to a single CPU core due to the static nature of the pipeline, hence limiting the throughput that can be achieved. In general, resources that can be used for network layer processing are limited by the number of connections. Ideally, the network stack should be able to dynamically scale the resource allocated for network layer processing independent of the number of connections. Overall, for both long and short messages, the network stack is unable to fully utilize the underlying hardware because of its static and dedicated nature. Long flows need more resource for interface level processing, and the short flows need more resource for network layer processing. In general, different applications can have bottlenecks at different parts of the pipeline. Hence, an ideal network stack should be able to independently allocate resource to different applications at a different stage of the pipeline, but this is not the case today. In the next example, we have two applications, the R app, which is a latency-sensitive application sending small messages, and the T app, which is a superbound application that's sending a long flow. Both of these are sharing the same CPU core. The following example shows the tail latency observed by the L app. Well, the L app in isolation, it sees microsecond scale tail latency. However, when collocated with T app, there is a 56x factor inflation in tail latency, and it jumps to the millisecond scale. This happens because the network layer processing for a given pipe is coupled to the application core. Here, since the applications are running on the same core, the network layer processing for both applications is also performed on the same core. As a result, processing for the L app can get blocked behind processing for the T app, hence causing latency inflation. Our ideal network stack should decouple network layer processing from application cores and be able to separate processing of L app from that of T app if sufficient host resources are available. In summary, today's network stack architecture are not able to fully exploit the capability of today's hardware. To make things worse, hardware is continuing to evolve. For network with link speed of 100 gigabits and higher, several recent work have shown that the bottleneck has shifted from the network core into the host. Dedicated, tightly integrated static pipes were a good fit for the internet and early generation data center. However, in this new regime, as the link speed continues to increase, today's network stack are on the brink of the breakdown. Hence, a re-architecture is inevitable. To that end, let's look at NetChannel, a new architecture for host network stack. Our key idea is to disaggregate the packet processing pipeline into separate loosely coupled layers. In particular, instead of having dedicated resource for each pipe, different pipe should be able to share resource. Instead of a tightly integrated pipeline, we like different parts of the pipeline should be decoupled both from application and from each other. Finally, instead of static pipes, it should be possible to independently scale the resource allocated to a pipe at different parts of the pipeline. It should be possible to do this dynamically based on other coexisting pipes and the resource availability at the host. NetChannel is our realization of this idea. NetChannel decouples the host network stack into three loosely coupled layers: the VNS, NetScheduler, and NetDriver layers. Let's first look at the virtual network assistant or VNS layer. The primary responsibility of the VNS layer is to provide application virtual interface, for example, the socket interface, so that the existing application can run without any modification. Data submitted by the application and the data received from low layer is stored in the virtual socket buffer. The VNS layer ensures the correctness of the virtual interface semantics. Second, the VNS decouples interface level processing from application cores by maintaining per core interface level processing threads. Interface level processing for any application can be done at any of these threads. Let's now look at the bottommost layers, the NetDriver layers. This layer abstracts away the network and the remote server as a multi-queue device. The queue of this device are channels, and this is abstraction that's provided to the upper layers. Each channel is an independent pipe of an underlying network transport. For example, with TCP, each channel would correspond to a single TCP connection. Channel can be implemented on top of any network transport, and the integrated new transport is essentially equivalent to writing a device driver for this multi-queue device. The net driver decouples network layer processing from the rest of the architecture. The mapping of data from virtual interface to channel is controlled by NetScheduler. For example, data from a single virtual socket can be multiplexed across multiple channels. Also, a single channel can be shared by multiple virtual sockets. The NetScheduler framework allows implementing flexible scheduling policy to control the mapping. This concludes the end-to-end architecture of NetChannel. Let's now look at a simple example of NetChannel's end-to-end operations. Say the application uses a socket interface which want to send 2 packets worth of data. Currently, there are 2 channels between their pair of endhosts. The first step is interface level processing. Here, that entails copying data from the application buffer to the virtual socket buffer. This data copy can be parallelized across multiple cores at the VNS layer. Now the data is mapped from the virtual socket to the channel by the NetScheduler. In this example, each of the packets is mapped to a different channel. Now the packets are transmitted through the channel of the network to the remote host, where they are demultiplexed from the channel into the remote virtual socket. Since the packet was sent over different channels, they can arrive out of order, as in this example. To ensure that the data is delivered to the application in the correct order, the packets are properly reordered at the VNS layer. Finally, the data is copied from the virtual socket buffer to the remote application. This, again, can be done parallelized across multiple cores. Now, let's look at an example which illustrates one of the challenges that NetChannel has to address when multiplexing data from multiple virtual interfaces on the same channel. Here, we have 2 applications. Data from application 2 is sent only on one channel, while data from application 1 is multiplexed on both channels. Consider the following scenario at the receiver side. Say that the application 2 virtual socket buffer is full. For example, if the application is busy with some other processing, due to this, the packet at the head of the channel cannot be dequeued. As a result, application 1's packet are head of line block behind application 2's packet, despite the fact that application 1's virtual socket has free space. To avoid such line blocking, we maintain per virtual socket response queue associated with each channel. Packets are first dequeued from the channel to a corresponding response queue, and then move the virtual socket buffers once it has free space. This helps unblock applications once packet. It's possible that the response queue gets filled up, causing the channel to get blocked again. This will trigger the underlying transport flow control applying back pressure on the sender caused the sender side channel to eventually fill up. When this happens, the sender side net scheduler will stop using this channel for applications one data and continue to use the other channel. This makes an enable NetChannel to handle transient hand-offline blocking. If the problem persists for long time scales, then we use a virtual socket interface level flow control mechanism. For more details, read the paper. Now, let's look at the NetChannel evaluation. We implement a prototype NetChannel as a kernel module in Linux and evaluated it with many different workloads. For the full detail of our evaluation, please see the paper. Here we focus on demonstrating that NetChannel achieves new optimal points, new operating points, saturate 200 gigabits using a single socket, scale short flow message processing super linearly, and achieve microsecond scale tier latency for LApp when co-located with TApps. We first run a single core application using a single socket to transmit the long flow. By utilizing 3 cores interface level processing at the VNS layer and 2 channel at the NetDriver layers, NetChannel enables Linux to saturate 200 gigabit links, and it's able to do so with minimal additional overhead in terms of a throughput per core. For short message, with increasing number of channels, NetChannel can enable linear scalability of throughput by scaling the resource allocated for network layer processings. To show NetChannel's performance isolation benefit, we co-located one LApp and 8 TApps on the same NUMA node. Here, NetChannel creates a use separate channels for LApp and TApps processing and map them to different CPU cores. This allows to separate network layer processing of LApp from the TApps and hence enable significantly lower tail latency of the LApp. Here, it's able to maintain microsecond scale tail latency even in the co-located case. We believe NetChannel is only the first step in the re-architecture of the host network stack for the Terabit Ethernet regime. There are many exciting directions for future work. This includes realizing new text driver policies, integration of a new transport protocols at the NetDriver layers, and realizing NetChannel as an idea in user space and hardware network stacks. To fuel further innovation along this direction and others, we have open source the NetChannel code. With that, I conclude and I will be open to take any questions. Thank you.
Well, I see it's easier online, so I think maybe there is even some of the courses here. So do you have any questions?
Thank you for your talk. So once you create the channel and you distribute your packet between the different channels, it means that probably the hash on the network will be different, which means that you might be reaching a high degree of out of order. It's nice when you have two nodes, but what will happen on a huge scale where you have thousands or hundreds of thousands of nodes, or in incast scenarios, what will happen then on your new architecture?
I think we don't get the sound.
Sorry, how about now? Cool. So first of all, channel still considered as a network connections. So it's a one-to-one connections. And in the reality, when we have the thousands of servers, how to create the channels between two servers actually depending on the next scheduler. Next scheduler can decide the how to create a channel based on the queue size of the each channel. So for example, consider a case when we observe, at the center side, when we observe a channel has a large queue size due to the network congestion, it can dynamically create a new channel. And for the incast scenario you just described, can you, do you mind just tell me more about why it could happen when we have a channel?
Okay,
more channels?
So I will clarify the first question. So you showed, for example, that you take 8 channels between 2 hosts. And it might be that a single application might distribute each packet on each one of the channels, meaning if each channel will take a different path, the worst case scenario is that you will receive them out of order, all of them out of order, right? And if you have a lot of application doing that, meaning you have like 100 applications or 50 applications running on the same host, each one of them will actually reach the out of order degree, the highest one, and therefore you'll start using buffers as you showed before, that you will move it to the side as a buffer. So on this case, it means that you will load the host. So when it's two hosts, okay, this is something that maybe we can we can allocate more memory. But what happened if the same host has channels from 1,000 hosts, and each one now will take a different degree of a different channel and different path, which will make out of order degree very, very large. The resources on your host probably will be done very, very fast.
So it actually depending on, if you're talking about the out of order packets, then essentially you need to limit the number of the channel being used for each application, and whether those channels are shared among those applications. So even if all the packets, let's say 8 packets are out of order, but if the ECMP, the per packet load balancing, is being used inside the network, then I can see those out of ordering is just very short time scale.
Okay, do you have more questions? So let me ask a quick question. So you decided to keep the socket interface, right? The advantages are clear, but what opportunities are there by rethinking this assumption? If you do something else, not sockets, can you gain something what you don't get now in NetChannel?
That's actually a great question. So, in our talk, we mainly use the socket example, but in reality, we can also support RPC interface in NetChannels. And when we use RPC, we can see RPC still has very high overhead in terms of serialization and deserializations. And by parallelizing the serialization, deserialization among multiple cores, we can see the benefits of using NetChannel.
Yeah, I think, thank you.
Cool.
Okay, I don't see more questions. One more question, last question for the talk.
Thanks for your talk. What are the benefits of corner-based I/O approach like yours compared to the user-level I/O, which accomplish very low latencies?
Sorry, do you mind repeating your questions? I didn't hear clearly. And what's the?
Yeah.
And can you just tell me what's the takeaway of the interface you just mentioned, or the system you just mentioned?
So what are the benefits of corner-level I/O approach like yours compared to user-level I/O? Because I know many user-level I/O networking stacks achieve very low latency, like a few microseconds. And I see your work shows like 100 microsecond latency. So I want to know the benefit of kernel-level I/O approach.
I see. So first of all, yeah, kernel approach will have high latency comparing to the user space approach. So the second thing is for the NetChannel, we can implement the NetChannel. Since the NetChannel is just essentially architecture, the key takeaway is scaling and scheduling resource dynamically. And so you can certainly imagine we implement NetChannel in the hardware inside the user space. So I can envision that improving existing user space under the NetChannel architectures may improve the performance for the user space stack as well. Okay, thank you. Shisha, looks like you and your courses got stuck still in the SIGCOMM' 2019 in Beijing. So thank you. Thanks, the presenter.